In this screencast, we'll introduce the concept of random variables, and especially normal random variables, which is where we'll focus most of our attention. A random variable, we use X, capital X to denote it, is a numerical outcome of a random event. So suppose you roll a die. X is the number that you get. Or you flip a coin 100 times. X is the number of times the coin comes up heads. Or you invest in a portfolio of stocks and bonds. X is the return on investment next year. Choose a random order at Amazon.com. X is the dollar amount of the order. There are two kinds of random variables, discrete and continuous. In discrete, there's basically a finite number of things that can happen. You roll a die, there's 6 possibilities. A continuous random variable is one in which you could get any number in some range. So in an investment portfolio, you could get any return between negative 20% and positive 30% or something like that, including returns of 2.457%, at least if you can measure accurately enough. So continuous random variables, we talk about ranges rather than individual outcomes. And with random variables, we care about what are the outcomes, what numbers could we get, and what's their probability. We care about the average, called the expected value, and denoted E of x, and also how variable they are. Usually we talk about the variance, V of x, and that's the square of the standard deviation. For example, with a stock investment, the variance tells you how volatile or risky your stock investment is. A large standard deviation, a large variance, means that, yeah, your stock or your investment could bring in a lot of money, but it also might lose you a lot of money. So, simple example of a discrete random variable, you roll a die, the outcomes that called the xi, 1, 2, 3, 4, 5, or 6, those are the things that could happen, and the probabilities, p sub I, 1, 6, 1, 6, 1, 6, all the way down the line. Very simple for discrete. The expected value and the variance for discrete random variables, we'll save it for homework if we do it at all. We won't need those concepts much in this course, but the School of Business uses them down the road. Now for continuous random variables, the story is a little more complicated. So here, the random variable is a randomly chosen real number between 0 and 10. So we're not talking about just 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10. We're talking about x has a possible value of 2.3759 or 6.14. So in that case, you don't talk about the probability of a particular outcome, you talk about the probability of a range. So this picture shows the possible values of x on the x-axis, 0 through 10, and we've got a height of 1/10 here, 0.1, so this whole area under the curve is 100%. And the probability that x is in some range is given by the area under this straight line over that range. That's kind of complicated, so let's just look at an example. What's the probability that x is some number between 2 and 4? Well, between 2 and 4, that's a distance of 2. The height is 0.1, so this area is base, 2 times 4 times the height, or length times width, which is 2 times 0.1, which is 0.2, or 20%. That makes sense. If you can get any real number between 0 and 10 and everything's equally likely, then since the range between 2 and 4 is 20% of that area of the range between 0 and 10, there ought to be a 20% chance that you get a number between 2 and 4. Now, the most important continuous random variable that we'll talk about is the normal distribution. That's the classic bell-shaped curve. And it gives a very special random variable, and we'll see how special and important it is in all kinds of ways. So here's a picture that shows orders at some online store where the mean is $400 and the standard deviation is $50. And here's our classic bell-shaped curve. If you had thousands of orders from that store and made a histogram, it would fit pretty well under this curve. So here's the mean at 400. Here we see it stretching out. Most of the action is between 250 and 550. That's 3 standard deviations on either side of the mean. And we're thinking of this area as being 1 or 100%. And to find the probability that an order is in some range, we're asking, okay, what's the probability, or what's the area under the curve in that range of x's? Now this is a theoretical distribution. Nothing fits it perfectly, but lots of things fit it well. And it can have any mean and any standard deviation, but they all share important common properties which lets us deal with them and answer questions. They're very important because many natural phenomena, things that just happen naturally, like the height of people, or the amount of, or the weight of a 1 pound loaf of bread coming off, a baker's assembly line. It's not going to be exactly 1 pound. There'll be some variations around 1 pound, but it'll be a normal distribution. So given any normal distribution, we can find the z-scores. And the z-scores always follow what's called the standard normal distribution with mean 0 and standard deviation 1. So you can take any data set, and if you look at the z-scores, you get a new data set with mean 0 and standard deviation 1. And we can answer questions about any normal distribution by standardizing, by finding the z-scores. And in particular, the Excel function norm.s.dist gives us the proportion of the standard normal distribution that's less than that z. And remember how to find z. You take the observed minus the mean over the standard deviation. So this is pretty wacky. Let's look at an example. So at our online store where the mean is $400 and standard deviation is $50, what proportion of sales are for less than $460? So here we have shaded in the region under the curve where the sales are less than 460. And we're asking ourselves, okay, what proportion of all sales are in here? What proportion of the area under the curve is shaded? 460 and less, what fraction of this total area is shaded? It's clearly more than 50%. That makes sense since the average is $400 and we're looking at 460, but what is it exactly? So first, we standardize. We find the z-score for 460. 460 minus 400 over 50 is 1.2. Then we go to the Excel function, norm.s.dist. Here's the 1.2. And true, it wants true for technical reasons. Don't worry about it, but just always put in true. And we get 0.88. So 88% of orders are for less than $460. What percentage are for more than $420? Well, we find the z-score that goes with 420. We get 0.4. Put that into norm.s.dist. We get 0.66. Now, norm.s.dist always tells us the percentage less than. Since 66% of orders are for less than 420, the remaining 34% must be for more than 420. So when we're talking about more than, you'll use norm.s.dist, but you'll subtract from 1 or from 100%. What proportion of orders are between 380 and 420? Well, now we need to find two z-scores. So here's the shaded region, 380 down here, 420 here. For 420, the z-score was 0.4, as in the last slide. For 380, it was negative 0.4. Now we find the norm.s.dist for each and subtract. Why do we subtract? Because the negative 0.4 tells us what percentage are below 380. The positive 0.4 gives us the percentage that's below 420 when we put them into norm.s.dist. And so when we subtract, the difference will be what's between them. And that's how we get to 31%. Always, always, always sketch a curve and shade in the area corresponding to what you want. This will help you avoid mistakes. Now, what if you know the percentage and you want to know x? At our store, how large does an order have to be in order to be in the top 5%? We'll take that up in the part 2 video.